So I will continue topic number 7 from the previous lecture plus with the number part 2. Okay, so I'll be sharing my screen right now. Okay, last time we stopped at this slide. Okay, so I will continue from slide 21. Okay, how about heat of reactions? Okay, which is H. Rx. The molar enthalpy of species I at a particular temperature and pressure, given denoted with Hi, is usually expressed in terms of enthalpy of formations of species I at some reference temperature Tr. Okay, so remember, please don't get confused between Hi, or sometimes they also use HIT. All right, with the HI not there, TR. Okay, so this one actually is referring to the standard temperature, which is 298 K or 25 degrees Celsius. Okay. Plus the change in enthalpy, delta HQI, that result when the temperature is raised from the reference temperature TR to some temperature T. Okay, so this would be to any T, any temperature. Okay, so this one, okay, from this until this statement referring to this one, HI not TR, and delta HQI is this one. Okay, so delta HQI, this one, we can expand the equation in terms of heat capacity. Okay, denoted with CP. Alright, for a system with no phase change or single phase reaction, this term can be replaced with the integration of the CP with respect to the temperature. Okay, so this would be the unit for the CP. So just substitute the delta HQI into this and it will become HI, okay, the enthalpy of formations of any species of I at any temperature is equal to the enthalpy change, alright, at the standard temperature ataupun reference temperature plus with the integration of the heat capacity. Okay. Or sometimes you will see, alright, how if they expand this equation, it becomes, okay, this equation, it becomes like delta HRX, okay, temperature at Rx is reactions, okay, is equal to delta H naught Rx. Okay, remember if there is not here means that it is in the reference temperature, okay, plus with the delta CP T minus TR. Okay, so this equation can be expanded into this one. Okay. So recall equation 11-16. Okay, we have a Q minus WS, okay, workshop. This is heat being applied plus Fn naught, right, to the summation of the theta Hi naught minus Hi, okay, minus delta HRX T Fn naught X, okay. So for inlet and outlet. To calculate the change in enthalpy, which is Hi minus Hi naught, when the reactant fluid is heated without phase change from its entrance temperature, Ti naught, we integrate equation 11-19. Okay, so this equation can be integrated, right, to represent Hi minus Hi naught. Okay, so this one can be equal to the Hi naught TR at the reference temperature plus with the T to TR CPI dt, okay, minus with the Hi naught TR plus Ti naught TR CPI dt. Okay, so the difference would be this one. Okay, so this one can be cancelled. That's why it become only from T to Ti naught. Alright, from the inlet, alright, T0 to any temperature. Okay, CPI dt, and then once you integrate it, it becomes this simpler form. Okay, so this one you can replace it in terms of the CP. Okay, so it becomes this equation. Okay, so steady state. Okay, let me move this one. Steady state energy balance for single phase chemical reaction with constant heat capacity is represented with this new equation 11-22. Okay, whereby you substitute the value of the heat capacity here, right? Which represent the HI0 minus HI. Okay, so we move on to this one. Okay, remember this is the heat of reaction at certain temperature. And delta H0 RXTR is at the heat reaction at the reference temperature. Okay, so this is the for a steady state single reactions, this chemical reaction, constant heat capacity system. Okay, so delta HRXT, all right, is equals to this is the enthalpy, okay, for the product. Okay, sorry, the product, and minus with the reactant. Okay, make sure you times with this one, the stoichiometric coefficient. Okay, where the enthalpy of each species is given by, okay, so this is for HIT, okay, is equal to HITR plus with this one. Okay, this one I already mentioned to you. Okay, so this is delta H, okay, RXTR, and this one is delta HRXT. Okay, so delta HRXT is equal to delta HRXTR plus VCPI T times TR. Okay, so this one same as this term. Okay, so when you expand this one, okay, this would represent this equation plus with the CP, this one, heat capacity, for this one. This is for the second one. Okay, so this is the first one, and this is the second one. Okay, so the second one you have to expand, okay, according to the species. Okay, so you have to take it out for the, this is the product, okay, minus with the reactant. Okay, so times with the T minus TR. Okay, this one. Okay, so you have to calculate for the heat of reactions, okay, as well as the what do you call it, difference of the heat capacity. Okay, this one is CP. Okay, so you have to have this thermodynamic data. Okay, then you will have able to calculate the heat of reaction at certain temperature. Okay, so equation 11-26 give the heat of reaction at any temperature in terms of the heat of reaction at a reference temperature, usually 298 K, and the CP term. Okay, this is the one. Okay, so let's say the example is for ethane cracking. Okay, so this is A to B plus with the C. Okay, so how do you get the heat of the reactions at a T reference is equals to, okay, so this is would be the C2H4, which is 5.28. This would be the product. Okay, enthalpy minus with the reactant. Okay, make sure you don't omit the value of negative here. Okay, because if you omit this negative, this would be positive. This would be negative. Okay, so make sure you get the right sign. Okay, so this is the value of the delta HRXN, which is positive 136.94. Okay, so the positive sign here indicate this is the endothermic reactions which need heat. Okay. So for the second one, okay, this is the reactions for the methane oxidation. Okay, we have the stoichiometry 1, this one 2, this one what do you call it, 1, and this is 2. So this is A plus with the 2B is equal to 2C plus plus with C plus 2D. Okay, so remember, plus you should write first the product, okay, with a plus here, minus with the reactant. Okay, so the answer would be, alright, the delta HRXN TREF is equals to negative 798.9 kJ/mole. Okay, so this is to get the reaction at TREF. Okay, let's say you need to get reactions at NET. Okay, you need to use the previous equation, which is delta Rx at the TR, okay, plus with delta CPT minus TR. Okay, so you have to use this one kalau nak cari heat of reaction at NET. Okay, so you need to try by yourself, for example 11-2, okay, in the formula, and also or example 8-2 if you use fourth addition of formula. Okay, then check the solution. Okay, so that's the end of the part 1. So move to part 2. Okay, so part 2 is about adiabatic operations, CSTR, okay, adiabatic equilibrium and adiabatic equilibrium conversions. Okay, so you need to get this X, okay, XE we call it. Okay, so don't get confused between the term of adiabatic, isothermal, and non-isothermal. Okay, so adiabatic, there is a change of temperature, but there is no change in heat. Alright, the Q is equals to 0. Okay, for non-adiabatic, okay, the Q is not equals to 0. Alright, the Q is equal to mCp delta T, whereby the heat is being supplied whether using cooler or heater. Okay, so this still applicable. That's why there is a term non-isothermal, which is there is a changes of temperature, and adiabatic reactor. Okay, so this define this what do you call it, terms. Okay. Alright, so you will get, this is what XE and X adiabatic lah. XE adiabatic. Okay, and usually adiabatic equilibrium, where we have the word equilibrium, means that you will measure for the reversible equation. Okay. Right. Okay, so then I don't have to explain this one. Okay, so move to this slide, adiabatic operations. Okay, sorry. Okay, so steady state energy balance for single phase chemical reactions is given by this equation. Remember the one that before this I dah preview about this one. And equation 11-26, okay, give the heat of reaction at reference temperature and also the CP term. Okay, so the energy balance in term of mean or constant heat capacity. Okay, so you just replace this one with equation 11-6. Okay, right, so this is for adiabatic operation. Okay, so this would be the assumption. Okay, the assumption is steady state energy balance for single phase chemical reaction with constant heat capacity. Okay, so if you can see this is equal to 0, means it is a steady state. So in most systems, the shaft work term Ws can be neglected. Therefore, for adiabatic system, equation 11 to 7 becomes this. Okay, so we can neglect this one since this is adiabatics, means that the Q is 0. Alright, and there is no work done by shaft. Okay, so you can cancel 0. So what remains is this one. Okay. So rearranging the equation above, we get conversion x or xb as a function of t. Okay, so this is this one. Okay, so basically you need to know the term for x and b. Alright, and then xeb and is equal to x. Okay, so actually this is the same one. This is conversion. It's just that x and b is you get it from the mass balance. Okay, and this one xeb is you obtain it from the energy balance. Okay, so you have a set of equations. You just rearrange it in terms of x. Okay, so how do you get xeb is you need to rearrange the equations. Okay, from this one. Okay, see you have this term x here. Okay, just put it at the right side here, then you will able to get this equation. Okay. So relationship between x and t for adiabatic exothermic reaction is given by the straight line here. Okay, this is applicable for all of the reactor. Okay, whereby the Q is equal to 0 and x equal to 0. Okay, so equation 11-29 can be rearranged to show temperature T as a function of conversion x. Okay, so from this one also you can put it this at the right side. Okay, so you can get two equations in terms of function in x or t. Okay, so this represents the x and the below one is represent the t. Okay, so this is how they expand the equations. Okay, so this graph is for the adiabatic exothermic reactions. Okay, so example, this is elementary irreversible liquid reactions. We have A to B. Okay, so the red law is negative RE is equal to KCA. So it is in liquid. Okay, assume this is in a CSTR. So given is CSTR. So first is you start with the design of equation according to type of reactor. In this case, is a CSTR. So V is equal to Fn0x over negative RA. Okay. So the right law would be the negative RA equal to KCA, whereby the K you have to refer to the Arrhenius equation, which relate with the temperature. Okay, so this is the Arrhenius equation for the red constant. Okay, then we have a stoichiometry for Ca, which is Ca is equal to Ca01 minus x. Okay, so you have to combine these three into one equation. Alright, V is equal to Fn0x over KCA0 1 minus x. Okay, so from here actually we have two cases. Okay, for the case 1, the x is specified. Okay, so if s is given, okay, you can calculate what is v and also what is t. Okay, and if the v is specified for case 2, you can calculate x and t. Okay, so once you know what is v, you can calculate x. Okay, and also you can calculate what is t. Okay, so actually t ni akan ceritalah macam mana you boleh what do you call it, relate with these two cases. Okay. Okay, so here actually we should have x and b, as I told you, is equal to s a b is equal to x. Okay, so this is for case 1. where X specified. So once you have the X specified, you need to calculate V and T. Okay, so we need to get the K. Okay, so if you can see here, the K is related with temperature. Okay, so in this case, T is not given, so you have to calculate it. So how you calculate the T here? Right, this T1 is usually referred to the initial one lah, T0. Okay, so you have to refer from the energy balance equation. Okay, the one that you already rearranged kan dia. Alright, so once you have the T here, you just put into the rate constant calculation equation. You will be able to get the rate constant value. Okay, so once you get the rate constant value, you will be able to get the volume. Okay, you know K, and then you have the value of X, and let's say it's given the Fn0 and Cn0, so automatically you can get the V. Okay, so let's say for case 2, V is specified, V is given. Alright, means that you need to get the XMB. Alright, so how do you get the XMB? Actually, it's from the mass balance. Okay, so you have to rearrange it. Okay, from the V is equal to Fa0 X over Ra. Okay, so which is Fa0 X KCA. Okay, this was negative, sorry, so it should be positive, equal to V. Okay, so Cn0 times V0. Okay, X over KCA. Okay, dalam kes ni dah kena so you boleh play around with this equation, alright, in term of tau. Okay, sebab you nak relatekan K. Okay, so the K will remain here. Okay, just replace K with Arrhenius equation. Okay, so daripada situ you will be able first to calculate what is the XMB. Okay, masukkan je nilai tau and K. Okay, and XEB is you dapat daripada, this is from the what do you call it, from the energy balance equation. Okay, just you arrangekan dia. Okay, so once you get the XMB, okay, you boleh dapatkan nilai XEB ni kalau you tukar the value of T. Okay, so once T berubah, okay, the K also akan berubah. Okay, sebab T akan relate with the K, the rate constant here. Okay, so same here, kalau you ubah T here, X ni akan berubah. Okay, so that's why nanti kalau you plotkan, you will have, okay, this is T, you kena varykan lah from the starting from the T initial until T final. Okay, and then you will have a set of the value of SMB and set of value of SEB. Okay, so you akan plot lah X versus T. So you have a straight line for the XEB, usually a straight line, and XMB ni depends on the the derivation ataupun how you rearrange the value. Okay, sometimes it will have straight line like this, sometimes dia akan menurun, depends. Okay, so you need to get, sebab the term the definition here is you need to get the equal SMB is equal to XEB, means that there is an intersection, alright, between the SMB and XEB. Okay, so you can plot and then you have this intersection. So you will have what is the T here and what is the X here. Okay, for adiabatic. Okay. So to further understand adiabatic operation in a CSTR, let's go through example 12-3, page 568 or 8-8 for Fogler fourth edition. Okay, so this is a very good example problem for you to understand adiabatic reaction in a CSTR. Okay, so this is a CSTR. Okay, it provides with the formation of Fa0 propylene oxide plus with the methanol. Okay, so there are two streams here. Okay, there is a premixer stream and then it becoming one, and then contact with the water, alright, before being introduced into the CSTR. Okay, so you have to measure what is T and X. Okay, So from here, okay, I just macam illustrate je lah apa yang benda ni. Okay, so let's say that A plus B is equal to C. Okay, this is a propylene oxide plus with the water, and you will have propylene glycol. Okay, the product here. Okay, so initially K is equals to A to the power E negative O RT. Okay, so how do you use this information? Okay, so now, okay, from the previous one, B is provided. Okay, means that this is case number 2. Okay, so this will be the case. First thing, as usual, starting with the more balance ataupun desired equation lah. Okay, so it depends on the type of reactor. Okay, so this is WFA naught X negative RA. Okay, so the red law, okay, sebenarnya dia ada description lah of the process. Okay, so I simplify the red law stated dia adalah K negative RA is equal to KCA. Okay, ini depends on the question lah. Okay, and then the stoichiometry. Okay, so in this case, this one will equals to V naught. Okay, because this is in CSTR, so automatically CA is equal to CA naught 1 minus X. Okay, so you have to combine this, okay, in order for you to relate the information ataupun value yang dah diberi dalam questions. So we have V is equal to FA naught X, okay, K is CA naught 1 minus X, okay, whereby you can simplify this one. This one is CA naught V naught, okay, so you will be able to get V naught X, okay, 1 minus X, okay. So as you know, tau is V over V naught, okay, alright. So from mass balance, remember we have the term S and B, okay. So S and B is tau K, okay, this is the one I dah simplify lah. 1 plus tau K. Okay, so this is the one. Okay, so macam mana you nak dapat ni? Tengok balik dekat topik number 4. Okay, alright, and then this one tau K kita akan replacekan dengan E negative RT, and then 1 plus tau K adalah E negative RT. Okay, so remember sekarang SMB is equal to XEB is equals to X. Okay, so you have to do the next one is to get what is XEB. Okay, XEB is the conversion from the energy balance. So from the algorithm, after you combine it, you do extra calculation for energy balance. So this is adiabatic. Okay, so Q is 0 and we assume WS is equal to 0. Okay, so XEB is equal to theta I CPI T minus TI naught. Okay, over with the delta HRX TR plus with delta CP T minus TR. Okay, alright. So T I naught actually is given from the questions. Okay, T pun dia dah beri juga, T dia tak beri, kita kena cari. Okay, so you kena cari all this kind of information. Okay, so starting from, kita settlekan this one. Okay, so E theta I CPI is equal to, alright, CPA plus with the theta B CPB plus with the theta M CPM. Okay, so this is for the reactant, okay, plus with the product. Okay, so this is methanol. Okay, and this is what do you call it? This is water just now, and this is ethylene. What do you call it? Ethylene apa tadi? Propylene oxide. Sorry, propylene oxide. Okay, kenapa? This one you don't have to consider for product. Okay, remember kalau theta I, okay, let's say the product is theta C. So theta C is equal to FC naught over FA naught. Okay, at time 0 there is no product. Okay, so that's why dia akan kosong. So that's why this part we only consider for reactant. Okay, so just put it the value here. Okay, carilah dia punya theta ni and you will get this one. Okay, and then theta HRX. Okay, for this part. Okay, so you kena kembangkan dia. Okay, expand the equation which is equal to H untuk C minus with the H, B minus with the H, A. Okay, so daripada sini you kena ada enthalpy dah, heat of reactions. Okay, kita tak consider methanol sebab methanol dah mix dengan H2 dengan propylene oxide. Okay, dia become excess yang kat sini. Okay, so and then another one you kena cari delta, okay, delta HRX T, okay, equals to delta HRX TR plus V delta C T minus TR. Okay, so daripada sini sebenarnya you nak cari nilai T nanti. Okay, so itulah cara dia. Alright, so once you get the nilai T and Ti naught, okay, T dia akan cari daripada sini lah equation ni nanti. Okay, dia play around with T ni. Okay, so once you get the T, just put it here and all the information here, you will be able to get what is XAB. Okay, and you boleh plot lah. Alright. So nak tahu details, try to tengok pada example ni. I just tunjuk general method sahaja. Okay, so summary of step to solve adiabatic. This is for CHR. Okay, problem. You can refer to table 12-3 for 5th edition and table 8-4 for 4th editions. Okay, so we have A and B whereby the case for the specific X and specific T. Okay, so this kita can label as case 1 lah. Okay, and then this would be the case 2. Okay, so X and B conversion calculated from the mole balance. Okay, and XB is the conversion calculated from the energy balance. Okay, so the intersection here, okay, yang bertembung SEB dengan SMB, and the mole balance in the figure give the steady state CSTR exit conversion and temperature. Okay, so you akan dapat what is the X, alright, and the T at the steady state, alright, of the exit conversion of the CSTR. Okay, so for example, in this exercise, okay, A to B and so on. Okay, so this is for case 2 whereby the volume is given. Okay, case 2 lah, so volume dah baru beri. Okay, look at this one lah, B. Okay, sekarang konsep pada B. Okay, so once the volume is given, alright, so you can follow these steps. Okay, in order for you to generate this curve. Okay, so try to get the intersection here. Okay, kalau katakan tak dapat juga, you kena turunkan dia ke bawah lagi temperature. Okay, until you have a point of intersection here. Okay, so from here, you can get lah what is the temperature and what is the X at the steady state of the conversion lah, of conversion and temperature. Okay, CSTR steady state. Alright. Okay, so we okay, saya rasa saya kena stop sini, sambung balik sebab takut very lengthy and the size of the recorded file is big.